Okay, this video is the AP review question number 2. So, what is the overall equation? So this is showing a reaction mechanism. Here they're giving you the equation for step 1. Okay, remember each hump represents a step, and step 2. So the overall reaction is basically if you just add the equations from step 1 to step 2 together, but crossing off any thing that crosses off, which would be like an intermediate in this case, it would cross off. So basically what you get is you get H2 plus, we have ICl and ICl, so there's two of them. So ICl, there's two of those, and that's going to make 2 HCl plus I2. Now your equation should be balanced if you did everything correctly. Okay, next thing is identify the slow step. So to figure out which step is the slowest, it's the one that has the greatest activation energy. So if you could kind of estimate the activation energy is basically for step 1, it's right here to the top of the peak. So that's the activation energy for step 1. And then step 2, oops, my drawing isn't too good, is from here to here. And so you can see that the activation energy is greater for step 1. So the slow step is step 1 is the slow step. So step 1, and because it has the greatest or greater activation energy. So the greater the activation energy, the slower the step. Okay, so step 1 is the slow step. Now you can get the rate law from the slow step if you know the slow step, as long as it doesn't have an intermediate in the reactants here. So the rate law is going to be rate equals K, and then it's just H2 to the first power times ICl to the first power. So that's the rate law. Okay, determine the sign of the enthalpy for step 1 and step 2. I'm going to go to a different graph, or the same graph, but I blew it up a little bit. So basically, the enthalpy change for step 1 is how much energy does it have when it's starting versus how much energy it has at the end of that step. So in between these two, for step 1, that's going to be your delta H for step 1. And if you can see that here's the energy to begin with, here's the energy at the end of step 1, and you can see that it has more energy at the end than it did at the beginning. So energy must be going in, so it's endothermic. Okay, endothermic, because it has more energy than it started with. Okay, and then for step 2, here's the energy where step 2 starts. Here's the energy when step 2 ends. And so the amount of the energy difference in between these two would be the delta H for step 2. And you can see that here's how much it has, and then it has less energy at the end, so some energy must have went out. So that's going to be exothermic because there's less energy at the end. Now, overall, you just take the energy at the end versus the energy at the beginning, and that is your delta H. And you can see that there's more energy at the beginning versus less energy at the end, so it is exothermic. So okay, so step 1 was endothermic, step 2 exo, and overall it was exo. Basically you're looking at the energy at the beginning versus at the end, and if there's more energy, or if there's less energy at the end, some energy must have went out to the surroundings, so it's exothermic. Okay, identify any intermediate or catalyst. Well, I already crossed off an intermediate. An intermediate is a substance that's produced in an earlier reaction and then used up in a later reaction. It doesn't show up in the overall reaction. So HI is an intermediate. There are no catalysts in this reaction. All right. Okay, now this one here it has to do with intermolecular forces. So identify the intermolecular forces in I2. So I2 would be just an I, and so remember in intermolecular forces, it says in I2, but it probably should be phrased between molecules of I2. Okay, and then ICl. All right, so here's ICl. So it's between molecules. What are these forces? Okay, well I2 is nonpolar. And so the only force between two nonpolar molecules are London dispersion forces. So I2 to I2 has only London dispersion forces. ICl, well remember everything has London dispersion forces. But ICl is a polar, slightly polar. So it's polar and this is polar. And an attraction between two polar molecules, as long as it's not hydrogen bonding, which it's not, it's a dipole force. Okay, so those are the forces. Okay, explain why the boiling point of I2 is higher than ICl. Well, since I2 has a higher boiling point, it must have greater intermolecular forces. So basically how I would explain this, I would say the London dispersion forces in I2 must be greater than the London dispersion forces and dipole forces in ICl. Okay, in general, the greater the intermolecular forces, the higher the boiling point or melting point. All right, so these forces, these LDFs, must be greater than the combination of LDFs and dipole-dipole in ICl because I2 has a higher boiling point. Okay? Now, identify the intermolecular forces in HI versus HCl. So here's HI, and here's another HI. So we're talking, when we talk about the intermolecular forces, it's the forces between molecules. And so HCl and HCl. Okay, well, whenever you have a hydrogen, you should think about hydrogen bonding, but this does not have hydrogen bonding. Okay, both have London dispersion forces. Okay, everything has London dispersion forces. All right, but HI is a polar molecule, and this is a polar molecule, so the attraction between polar molecules is dipole-dipole. Okay, this doesn't have hydrogen bonding because remember hydrogen bonding has to have a hydrogen bond, it has to be, you have to make a hydrogen sandwich between F, O, or N, and there's no F, O, or N in these molecules. Okay, so this one is also dipole-dipole. So both have London dispersion forces and dipole-dipole. Well, why is the boiling point of HI higher than HCl? Okay, well, HI, each molecule of HI has more electrons. HI has more electrons than HCl, making HI, oops, I forgot the H, HI more, and here's a good word for you, polarizable. More electrons make it more polarizable, making HI more polarizable than HCl. All right, and so basically that's what gives it the higher boiling point because the more electrons make it more polarizable. All right. Okay, HI is formed by the reaction of H2 and I2 according to the balanced equation. Write the Kp expression. Okay, so your Kp is going to be the product, so HI, and that's going to be to the second power over H2 to the first power, I2 to the first power. Okay, this is telling us that the 1 liter vessel has a pressure of 1 atmosphere and 1 atmosphere of that. Calculate the final pressure at equilibrium. Okay, so whenever you get one of these like that, you want to make an ice table. And anyway, so we go initial, change, equilibrium. Okay, so a 1 liter vessel initially has a pressure of 1 atmosphere, so 1 H2 and 1 I2. Now there would be 0 of this if it hasn't started yet. Okay, now this one, as the reaction proceeds, it's going to go down by X. This one's going to go down by X. This one, however, is going to go up because there's a 2 there by 2X. So at equilibrium, we have 1 minus X of H2, 1 minus X of I2, and 2X of HI. Okay, so it's giving us the Kp is 50, so we know that. So now what we're going to do is we're going to plug in what we know from our ice table into this expression. So 50 is going to equal HI, which is 2X. Now that whole thing is squared, divided by 1 minus X times 1 minus X. Now this looks like a quadratic, but it really isn't to solve for X. So what you can do is you can square root both sides. So if I square root 50 and I square root everything over here on this side, let's see here, you end up getting the square root of 50 is 7.07 is going to equal 2x over 1 minus x. And then you can distribute the 1 minus x, so you get 7.07 minus 7.07x is equal to 2x. Okay, and anyway, you can do the math, but anyway, you solve for x, and x is equal to 0.78. And the units would be atmospheres because this is pressure. Now, what they want is the final pressure of HI at equilibrium. Well, at equilibrium, it's 2 times x. So 2 times 0.78 atmospheres would equal 1.6 atmospheres. Okay, the last question. How many moles of I2 remain after the reaction has come to equilibrium? All right, well, this is giving you pressure values, and they're saying that, initially there was 1 atmosphere to start with, but it's going to go down by, we just calculated that, it's going to go down by 0.78 atmospheres. And so at equilibrium, we're going to end up with about 0.22 atmospheres. Okay, so now we know the pressure at equilibrium. Now we can get the moles by doing a PV equals nRT. And we know our pressure is 0.22. Our volume is 1 liter. It's a rigid 1 liter, so 1 liter equals N, that's what we don't know, times R is 0.08206 atmospheres times liters, moles, Kelvin, times temperature. Now our temperature, this is giving us 450 Celsius. So remember, you have to add 273 because everything with gas laws has to be in Kelvin. So that's 723 Kelvins. Now, this ideal gas law, the R value tells you what units everything has to be in. So make sure everything is in the right unit. Okay, then you end up solving for N, and N equals 0.0037 moles is what I got. Okay, that's it for this video.